Welcome to another video in the Analog Techniques series. If you haven't watched part 1 of this video, I suggest you watch it first. In this video, we'll see another open loop technique by which the overall system bandwidth can be extended to some degree. The technique is simply to cascade identical amplifiers in series. To see how this cascade helps to increase the bandwidth, we need to look at the overall transfer function. Let's assume each of the amplifier has one pole at omega p and a DC gain of A. The cascaded transfer function can be simply written as the product of the gain of each of the stages, as shown here. Next, by taking the absolute value, we can get the magnitude response and find the 3 dB location. The 3 dB frequency location is where the magnitude drops by a factor of square root of 2 relative to the DC gain. After we solve this equation, we can find the system bandwidth omega tot as shown in this expression. The gain is also given simply as a to the power of n, and the GBW is simply the product of gain and bandwidth as shown here. One interesting thing to note here is that for large values of A, the rate of increase of the total gain is greater than the rate of decrease of the total system bandwidth with respect to n. This can be shown by plotting the normalized gain bandwidth product with respect to n. The normalized gain bandwidth product is simply the system gain bandwidth product divided by the gain of a single stage amplifier times omega p. Here is a numerical simulation plot of the normalized gain bandwidth product with respect to n for different values of A. We can see that for values of A greater than 1, the GBW increases with respect to n. So how do we use this property to increase the bandwidth? Let's assume that each of the amplifier stage is designed for a maximum gain bandwidth product of GBWn. The maximum achievable gain bandwidth product is limited by Ft of the MOSFET, which depends on the technology process. Also, let's assume that the required gain is equal to A tot. Then the stage gain becomes A tot to the power of 1 over n, where n is the number of stages in the cascade. The maximum stage bandwidth is also given by GBWm over As, which is the stage gain. Now, by using the expression that we derived before, we can find the total system bandwidth as shown here. In this expression, GBWm is fixed for a design and technology process, but the second term is a function of n and is subject to optimization, meaning that there is a particular value of n where the term attains the maximum value. Now we'll not go into the maths, but from basic optimization theory, we can simply take the derivative of this expression with respect to n and equate it to 0. And then we can get the optimum value of n, which is shown here. Now, to check whether this value actually helps to increase the bandwidth, we consider a design example. Let's say we need to design an amplifier with a total gain of 10, and given that each of the amplifier stages can have a maximum GBW of 10 GHz. So the bandwidth of this single stage amplifier will be 1 GHz. Now let's consider a multi-stage amplifier design where the specifications for the gain and GBW are the same, but we can use n number of stages. From the n optimum equation, we get the optimum value for n, which is 4 in this case. Using this value, we can then find the stage gain as 1.78 and the stage bandwidth as 5.6 GHz. We can use the system bandwidth expression to find the total system bandwidth as 2.4 GHz. So we see that using 4 stages, the total system bandwidth is more than doubled. However, the trade-off here is that we need to burn 4 times the power consumption. Hence, in an actual design, often the power consumption is also taken into account, and usually a value smaller than n opt is used. This is an example of a real design published in this paper. It uses 3 stages, and in each of the stages, we can see there is some sort of passive bandwidth extension technique applied. If you have seen part 1 of this video, you'll be able to identify these techniques easily. For example, the first stage uses T-coil peaking, and the second and third stage uses a combination of bridge shunt peaking and series peaking. So that's it for this video. If you want to see more videos like this or want me to cover other topics, please comment below and subscribe to this channel. Thanks for watching and see you in the next one.